Alright, so our next problem states that for a binary mixture of 1 benzene and 2 toluene, write a Python function for calculating the dew temperature and pressure and bubble temperature and pressure. Generate the plots of the binary vapor-liquid equilibrium phase diagram at a constant temperature of 393 Kelvin and another at a constant pressure of 150 kilopascals. So I've included a picture of the equations that we derived in the last video, and so now first thing we're going to want to do is write Python functions to calculate these. So open up a new Python window, and first thing we need to import our libraries that we're going to use. So first I'm going to get this code over here, and this is the code that's going to calculate our vapor pressures using the Answin equation. So copy the link to that there, and then I can use the wget command and that link to get that code. So then that'll load in. Looks like it worked. So from that we're going to import CHE as CHE. Next we are going to want to import numpy. Then we're going to want to import and from SciPy optimize and import our root function. And then we're also going to need plotting, so from plotly subplots, we're going to import make subplots. Shift enter on that, and it appears to have worked. Alright, so then we're going to want to call in which compounds we're going to use. So remember we had benzene and toluene, so we use CHE props, and we just need to import an array of, or list of our compounds. So the first is benzene, and then the second is toluene. Alright, so let's start off with our bubble pressure. So we need a function, so we'll define our function and we can call it bubble P for bubble pressure. So then we need to define what our inputs are going to be. So if you look at this equation, we're going to need to know the mole fractions in the liquid phase, so that'll be X. And then we'll need to know our pure component vapor pressure, which will be calculated using this code that I've imported, and we're going to need to know the temperature for that. Alright, and then we just return the summation. So return np.sum of x times p.pvap of the temperature. Alright, so that's our function for bubble pressure. So dew pressure is going to be just as easy, so we'll do that one next. So define the dew pressure. For this one, we're going to need our component in the liquid phase, so we'll call that y. And then again, we're going to need to know T to compute the pure component vapor pressure. And then we're going to return this equation, so return, and then we'll have 1 divided by np.sum of y divided by p.pvap of the temperature. Alright, so there we got that one. Alright, so next let's look at the bubble temperature. So we can define a function, we'll call this one bubble T. And this time, what do we need to input? So we're again going to need to input the same thing because it's a very similar equation to bubble pressure. So it'll be X and T. And then, so for this one, since we're going to need to use a root solver for this, we're going to need a function within a function because root solver is going to look to solve a function. So within this function, we're going to find another function, and we can just call this define equation, yeah, just equation bubble T. So we'll call it that, and within this it will take in, it will take in the temperature. So up here we're going to need the pressure, because in this problem we know the pressure, we don't know the temperature, and then we're going to want to solve for the temperature. And then actually, since root solver is going to need a vector, we're going to have a vector, and then we can unpack this vector into our temperature. Alright, so then we can write out our equation. So our equation is going to be just like this summation part. So we'll have, so we'll return NP dot sum of, alright, so this is actually the same summation as up here. So I'm gonna copy that so I don't have to write it again. Alright, so then outside of that, we're going to then return root. And so first we have the, okay, so up here because we're gonna want to root this whole thing, so we're gonna need the pressure minus that. Alright, and then we'll want to root that whole equation. So first we'll ask for the function that we want to take the root of, and so we call that equation bubble T, and then it will take a guess, and our guess will be the temperature. Alright, so actually up here we have an error, and that's because this needs to be a guess. So our guess, let's just say, like room temperature, so we can have 298. So we can make that our guess. Alright, so then that's our equation for bubble T, and then let's do our due temperature. So define a function called due temperature. This time we're going to need, so we'll know P, we'll know the mole fractions in the liquid phase or vapor phase. We're going to want to solve for T. So similar to what we've done before, we're going to have Y and the pressure. Alright, and then like the bubble T, within it we're going to find another function. So we're going to call this equation due T. And we'll again import a vector, since that is what this wants, or what root wants. And so then we can unpack that vector to be T. So the first value is going to be T. It will only be a one value vector, but that's what root wants. So, and then we'll return this equation over here. So it'll be the pressure minus, and then it'll be the same thing that we had up here for the due pressure. So I'm going to put that in parentheses there. And then, so that's that. Then we're going to return the root of this, so return root of, so first we need the equations, so equation due T, and then we'll need a guess. Again, we can guess 298 Kelvin, and then we're going to want to take the first value, like that, and I forgot to do that up here. Alright, so nope, that's not how you do that. Do it without the, what? that. Okay, it's without the period. All right, so there we go. There are those equations or the functions that we're going to need to calculate the bubble pressure, dew temperature, bubble temperature. All right, so next thing we're going to want to do is plot these things, because that's the next thing it tells us to do in our problem. But first we should probably make sure that these functions work. So let's just do a couple. So we'll do bubble P, we'll just use 0.5 for now. These numbers don't mean anything, I'm just testing to make sure. Yep, that gives us a number. All right, let's try the same thing for dew P. Yep, gives us a number. And bubble P. So we'll use 0.5 as a mole fraction again. Pressure, we'll just do, and we can do what we were going to do for our thing, so, or for our problem. Okay, so then there's where we have an error. Oh, I didn't capitalize that. It's not where I started. Okay. Alright, and we get infinity. Oh, we already tested that one anyway. So that was probably just too high. It's bubble T we wanted to test. And, oh yeah, because that was, I typed in a pressure instead of a temperature, so there you go. Okay, so now we're getting an error here. And I think I still don't have this correct. So I think it's supposed to be .x maybe. Alright, there we go, that's where we're getting our number. So the syntax for that is .x 0. So let's just make sure that the do T also works. Do T. I didn't shift enter it. Ooh. Didn't shift enter up here. Alright, so now everything is working, giving us numbers. That's good. And so now we can work on plotting. So to plot, we're going to want to do this over a range of values. So we might start with, let's say Z1, just as a general for either X or Y, we don't really know, because we're going to use it for both. So that way I don't have to make a whole bunch of lists that are the exact same thing. So then we'll linspace these from 0 to 1, and we'll have 11 points. And so that'll just have us increments of 0.1, 0.2, 0.3, etc. Alright, so then we're going to want to define, well, we can first define what we know. So we know our temperature is going to be 393 Kelvin, and we know that our pressure is going to be equal to 150 kilopascals. So we have those. Then we're going to want to make lists that we can append things to lists as we calculate them. So let's just start with the one up top. So we got bubble P. So we're going to have bubble P and then list so it doesn't get confused with the function. And we're going to just have that be an empty list for now. And then we're going to do the same for dew pressure. And same for bubble temperature, so and dew temperature. Alright, so there are lists, and then we're going to want to use a for loop to append things to these. So for so then we can do for xy1 because we already use z, so we'll just use xy because we'll use it as both x and y in the range z1, so it'll do that for each of those. And then we'll have xy2 is going to be equal to 1 minus xy1. So that just means that the mole fraction of component 1 is 1 minus, the mole fraction of component 2 is 1 minus the mole fraction of component 1, which we know. Alright, so then we're just going to want to append all of our lists. I bet that needs that, maybe, not sure. Oh, okay, there it goes, it fixed itself. It was probably the cool one. Alright, so then we're going to want to append our list. So we'll start with bubble P, because that's what we have on top. It doesn't really matter which one we start with, but I'm just going to go in order. And then append. And then we're going to want to append our bubble P calculations. So it'll be bubble P, and we'll input our x's. So we're going to want to do that for both x1 and y1. So we'll want an array in here. And that array will be xy1 or xy2. Then outside of that, and then comma the pressure, right? Or no, for bubble P we need the temperature, so comma temperature. Alright, and then I'm just going to leave that at that. Alright, so it doesn't seem to have any errors, but let's just check, see what our bubble P list is, make sure that it added some values. Alright, so there you can see we've now got an array of what should be 11 values at the different mole fractions. Alright, so let's carry on. And so we're going to do this for the do-P list as well. And then we'll do do-P. And then we'll do the same thing that we did up here. So I'm just going to copy it, because do pressure is going to take in this xy value and then the t. So that's what I was meaning, that we're going to use it for both x and y, so that's why I did that. Alright, so then we're going to want to append to the bubble T list. And this time we're going to do bubble T. And again, we're going to have this array, then we're going to have this array, and then we're going to have the pressure. Another parenthesis there. Make sure with my copying all the parentheses got transferred over correctly. Alright, seems to have worked good. Alright, so then we're going to need the do temperature list, and we're going to want to append that. We're going to want to append our calculations for the do temperature, so we'll have do temperature of, again, this empty array, and then comma pressure, again another parenthesis. Alright, so now we have appended to all of our list, and one of these is not right. Do pressure, so yes, I do think the parentheses must have messed up somewhere. So we have that one, and this one goes to that one. I think I just have an extra set, but I don't need. Let's try that. Alright, so there we go. So there is our lists, and then we can plot them. So first we're going to want to make a figure. So a figure is make subplots, and we're going to want 1 row and 2 columns. And then we can have our titles equal to, so the first one, so we'll use F strings for these. So the first one, we're going to have a temperature equal to our temperature that we have in Kelvin. And then our second plot will be our pressure plot. So we'll have another F string. We'll have the pressure equal to the pressure in pascals. Alright. So next, we want to start adding our subplots, so we can fig.add scatter, and our x. So our x's for these are going to be, so x-axis we're going to want our mole fractions, so either x or y, so we'll use the z1 that we used up here. And then for our y-axis, we're going to want those to be our lists. So we can start with the bubble p list. So we're going to want this one on plot, so row 1, I'd like this to go away, column, so this is pressure, so it will go on our pressure plot, so that's column 2. And then, yeah, or we would want a name for this plot, and we'll name it bubble pressure. Alright, so let's shift enter and make sure that worked. Alright, there we go with it. So we can see our first plot's there. Here I can full screen this so it looks better. Alright, so then let's continue adding our plots. So I'm going to copy this so I don't have to type everything again because some of it will stay the same. So then next we can add our dew pressure. And right here. Alright, so there you can see our 2 curves on our pressure graph. Then this time we're going to want to do the temperature. And we're going to want this one in column 1, so it'll be on this plot over here. Alright, so there we got that one. And then we have one more to add. Alright, so this one will be our dew temperature. And name it after the dew temperature. Alright, so there we go. There are our 2 plots. So this one's plot of our temperatures. This one's a plot of our temperatures. This one is, oh wait, I flipped these. Because the ones that are calculating temperature, we know the pressure, so we need to flip the titles of these. Okay. There we go. Okay, so over here we know that the pressure is 150 kilopascals, and then we're calculating the temperatures. And so our green curve, this is our bubble temperature curve. So this is the curve at which our first bubble is forming, which means that anywhere below this, so any of these temperatures down here, we have entirely liquid mixture. And then this purple curve, this is our due temperature, which means the first drop of liquid that's forming. So above here we have entirely vapor. And then in between here we're going to have a mixture. So essentially, if you're at a mole fraction of 0.4 maybe, you're at 370 Kelvin, that means we're only going to have liquid to deal with. And then you can keep increasing this temperature, and then eventually you'll get here and your first bubble will form, increase a little bit more, and you'll have both vapor and liquid. And then eventually we'll get to this point, and that's when the last drop of liquid will turn into vapor when we're going this direction. And then above there we'll have all vapor, and then you can do the same thing in reverse. If we start up here at 400 Kelvin, we can decrease the temperature until we get to this point, and that's when our first drop is going to be formed. In the middle here, we will have a mixture of vapor and liquid, and then here is where it turns to all liquid. And you can do that for any mole fraction along here. And so that's that's the due temperature and bubble temperature. And then over here it's a similar deal, but this time we know that the temperature is 393 Kelvin, and we're looking at the pressures. And so this red curve, that's our due pressure, and so any pressure lower than that we know is going to be our vapor. So it'll go up here, and then this is where our first drop is going to form. Then we'll have a mixture of vapor and liquid, and then it will reach our bubble pressure curve, at which point it will become all liquid up here at high pressures. So these are our two plots that we can form for the bubble temperature, due temperature, bubble pressure, and due pressure.